So what we're now going to look at is what happens when the rates of increase of both types of a population are dependent on the numbers of individuals of that particular type. But this rate we're now going to call fitness. That's going to be the term we use. It's the fitness of an individual in a given population. And we're going to consider a general population X to be a vector x1 and x2, where x1 and x2 are the proportions of both types. And then we have two fitness functions, so f1 of x1, so that's the utility that an individual of the first type gets. It shouldn't be x1, it should be f1 of x. So given the population vector x, what is the fitness of an individual of the first type? And given population x, what is the fitness of the individual of the second type? And then everything else just follows as before, except that we have these fitness dependent things. So for example, perhaps the first type has a higher fitness if there are more individuals of the first type in the population. That's the kind of idea that we're dealing with here. And so we have dx1 dt is going to be equal to x1 times f1 of x minus phi, which is this thing that just ensures that we have x1 plus x2 equals 1. So we keep that. And we also have dx2 dt is equal to x2 times f2 of x minus phi. Because we have this, we can calculate the derivative of that. So we have that dx1 dt plus dx2 dt is going to be equal to, and now we just grab these expressions here, which gives us x1 times f1 of x minus phi plus x2 of x times f2 of x minus phi. And then we carry on, but we can substitute that x2 is actually equal to 1 minus x1. And we just write down that d of x1 dt, oh, forgetting the important detail, that's got to be equal to 0. And from this, we can obtain that phi is equal to x1 f1 of x plus x2 f2 of x. So that's extremely similar to the case we did in the previous chapter. Now, taking this, we just get that dx dt is equal to x1 times f1 of x minus, and now we have this expression, x1 f1 of x minus x2 f2 of x, which we can just write as x1 times 1 minus x1 times f of 1 of x minus f of 2 of x. It's very similar to before, and what we see is that we have 3 points at which this is going to be equal to 0. And so we have that this x1 is equal to 0, we have that x1 is equal to 1, and also we have a given population where the fitness of the first type is equal to the fitness of the second type. And that's the basic ideas behind frequency-dependent selection. And when we actually start talking about evolutionary game theory, excuse me, we have a matrix A that are just going to be our utilities. And the idea is that the fitness of individuals of the first type is given by the first row, and the fitness of the individuals of the second type is given by the second row. But what we have is that the individuals of the first type, their fitness, as a function of x, is going to be A times x1, because that's how many times they're going to get an A, because that's how many of the first type there are, plus B times x2. And similarly, we have f2 of x is equal to cx1 plus dx2. So this is what we did up here was kind of a general case for any given f's, but we're going to consider whether utilities are given by a particular matrix. And so we have this equation. That might be clear that can just be written as f equals a of x. These two things are the same expression. And then finally we can also get that phi is equal to f of x. And we know this is, sorry, I don't mean f of x, I mean f times x. If this is f, then we know that phi is just x1 times f1 and x2 times f2. And so this equation up here can actually be written in matrix form as dx dt equals x times f minus phi. Now, we've kind of gone from using calculus and differential equations to describe a thing, and now we've kind of touched back on to using a matrix. And what we're going to now see is how we can quantify our stability of these systems using the game notation.